This tutorial will explore the condensation module at the TRISCO application. We shall continue from the working file of the TRISCO grids and blocks tutorial. You can find the corresponding files from the link mentioned in the description. Ensure that your license includes a condensation module, then enable the condensation module from Settings. Once you enable it, you notice a column at the Colors window with mu value, which is the vapor resistance factor. By default, it's always 1 for all materials and doesn't reflect true mu value when you directly choose material from the color database. This is because the default color database only reflects thermal properties, not vapor ones. However, we can adjust the default color database and input vapor resistance factors to the colors for future use. We can manually change the mu value, say we input 1.2 for insulation. Alternatively, for concrete, we can input the mu value from the material database. Select concrete, then from the colors window, choose load material, from EN 12524 select CN concrete. Here you find reinforced concrete 2%, choose that, and then lambda and mu values will be displayed. Upon clicking OK, we notice that mu value is imported from the standards. Similarly, you could do the same for steel. From the Colors menu choose Load Material. Then from the list select EN 12524, select CN Metals, choose Steel, and click OK. Now for boundary conditions, to activate relative humidity we need to change the standard from EN 6946 to EN 13788 or nihil. Now you notice the relative humidity column is in editable format. But you need to note that since you changed the standards, you need to cross-check all the parameters. Here you notice external boundary condition thermal properties have been changed. If you choose it to be EN 13788, then when you reopen your TRISCO project file in future, the condensation module is automatically activated, whereas, for nihil, you must manually turn it on each time you reopen this file. We shall choose EN 13788 for both boundary conditions. For color 170, we should change the subtype back to He and temperature to 0 degrees. For relative humidity, for exterior can be 80% and the interior as 60% for this exercise. From the top toolbar, choose Calculation Parameters. Navigate to the Condensation menu. Here you find the settings to perform condensation analysis. Here, we will choose to calculate interstitial condensation only at the material interfaces as per ISO 13788. Here, we define what percentage of the simulation nodes exceeding its saturation vapor pressure is fixed during each iteration. A lower percentage will lead to more accurate results but a longer simulation time. Hence, for any new users, it's suggested to use 10% for the right balance. We need a refined grid to perform analysis. From the Grids menu choose Auto Split. We have spoken about the Auto Split settings in the previous videos. You can let these default settings be as it's displayed here, then click on Calculate Interstitial Condensation on the top toolbar. This is located beside Calculate Thermal System. Once the analysis finishes, open the graphic output. What's new here while running condensation analysis is fill relative humidity and fill interstitial condensation rate, which is the result of the last instance of analysis. Then fill with accumulated condensation. To better visualize the result, turn on the material preview and clip insulation. Now if you choose to turn on fill interstitial condensation, then you can see areas on condensation zones, and when you hover your mouse on these zones you get to amount of condensation in a month. At the level of the thermal bridge, in the middle of this component, the temperature on the exterior side of the insulation is warmer, avoiding interstitial condensation for this example. The color gradient for the result you see here is only a relative color but not an absolute index. You will better visualize this in the later part of this video. We did not find any difference between interstitial condensation for the last calculation period and accumulated condensation as we performed analysis for just 30 days. Accumulated condensation analysis takes place for each month, which is approximately 30 days. Later in this video, we will perform an analysis for several months. We shall now modify the geometry by creating a slit on the interior side of the concrete wall to further explore interstitial condensation. From the Grids menu choose Minimum Grid, then choose X and Y for the axis to simplify. Select the last block with the color 13, which represents steel. From the Blocks menu choose Copy After. Now for the duplicated block modify Y-min to 3 and Y-max to 4 and change the color to 151 for insulation. Using the transform coordinates icon on the top toolbar, choose Translation along X with 20 cm. From the Grids menu choose Auto Split. Once the grid is ready, run the condensation analysis. Upon completion, open Graphics Output. Under Material Preview, clip insulation layer using Clip Color. Now choose Interstitial Condensation for the last calculation. Here you notice the color gradient relative to the maximum condensation zone. Since insulation has lower vapor diffusion resistance than concrete, a slit causes the vapor from the interior environment to pass through, causing higher interstitial condensation here. We will now run the analysis for several months. Close the graphic output from the Edit menu, choose Clip Colors and turn on the clipped layers. Now at the Colors window, under Subtype, double-click and change it to Clim E for exterior boundary conditions. For interior boundary conditions, change it to Clim I. You notice that relative humidity and temperature are a function of climatic conditions. Double-click on any of these cells, and then Monthly Mean Climatic Data shall open. Here you can set data for monthly mean exterior temperature, interior temperature, exterior relative humidity, and interior relative humidity. Set the data as per your local climate. For this exercise you can input data as shown in this video. Then, click on Calculate Interstitial Condensation, then choose Start Month as September as the start month, as ideally the wall would be dried out after summer, and choose the number of months as 12 for example. We now run the analysis and you notice the calculation is being run for all 12 months. Click on Text Output. Next, go to the Interstitial Moisture Accumulation tab. Here you see condensation or evaporation and net accumulation for each month of the analysis period. So, you notice that the interstitial condensation accumulated during the winter months has been fully dried out after summer. You can close the text output. Now, we will explore the situation for the month March. So, we recalculate the simulation for only 7 months. If you now open the graphic output and fill interstitial condensation with the last period, you notice graphically the condensation rate in blue and the evaporation rate in red for the last calculation period, which is March in this example. Now, if you fill with net accumulated condensation, you notice the net result due to evaporation and accumulated moisture at the end of March. Hope you enjoyed learning Trisco. Stay tuned to our channel and Physibel knowledge base for further updates. Feel free to reach out through the website in case of any inquiries.